Alright, so in this video we'll see concepts of more concepts regarding vector spaces and subspaces. In particular, we'll see notions of linear independence, what is the basis of a vector space, and what's the dimension of a vector space. So again, these are all concepts that you would have already seen at some point in one form or the other. But we'll give more formal. I'll give a more formal definition of each of these concepts. So what do we mean by linear independence? Suppose that we are given a set of n vectors. v1, v2, up to vn. Then, so all of these belong to some vector space defined over a suitable field f. So henceforth, I'll denote just for ease of notation. I'll use plus and dot to indicate vector addition and scalar multiplication with the vector. I'll also use plus and dot to indicate the addition and multiplication within the field, just for the sake of convenience, because drawing a square is a little more complicated, but hopefully there should be no confusion regarding addition within the vector space and addition within the field. So of course this is abuse of notation. The plus which represents addition of two vectors is actually different from the plus which represents addition of two field elements, but I'll nevertheless use the same notation. Okay, so we say that a set of vectors v1 through vn are which come from some vector space capital V. These are linearly independent if any linear combination. So if you look at all possible linear combinations, alpha 1 v1 plus alpha 2 v2 plus alpha n vn, if you look at all possible combinations alpha 1 alpha 2 up to alpha n which result in the zero vector, the only possible configuration which gives you the zero vector is the set of zero coefficients. So these are linearly independent if alpha 1 v1 plus alpha v2 v2 up to alpha n vn equal to 0 implies that alpha 1 equal to alpha 2 equal to alpha n equal to 0. So no non-zero linear combination of the alpha i's can get you to the zero vector. Okay. So obviously if alpha 1 equal to alpha 2 equal to alpha n is all equal to 0, then the zero linear combination always gives you the zero vector, but they are linearly independent if no non-zero linear combination can give you the zero vector. Every non-zero linear combination must get you some vector which is non-zero, right? And typically, how do you test for linear independence? You can again use sort of column operations. So to test whether a set of vectors v1 v2 up to vn, to test if v1 through vn are linearly independent, what you can do is you can either do column operations on the matrix formed by these vectors, or you can take v1 transpose v2 transpose. You can write each vector as a row vector vn transpose and then do row operations. Once you do row operations, if the number of non-zero rows is equal to n, then they are linearly independent. The number of non-zero rows is less than n, then they are linearly dependent, right? So the vectors are linearly dependent if some non-zero linear combination of of these vectors gives you the 0 vector, right? So for example, if you look at 1 2 1 1 3 1, these two vectors are linearly independent. However, this vector, so these three vectors put together are linearly dependent, because the third vector can be written as a linear combination of the first two. So the sum of the first two vectors gives you the third vector, right? So now that we've seen what linear combinations are and what do we mean by linear dependence and independence, let us see concepts of spanning sets and bases. So given a vector space capital V, we say that a set of vectors v1 v2 up to vn spans V, or this set is said to be a spanning set of capital V if every vector in the vector space can be written as V equal to alpha 1 v1 plus alpha 2 v2, so on up to alpha n vn for some for some coefficients alpha 1 alpha 2 up to alpha n. So for example, let's take R2. So can you think of, of course we know that 1 0 and 0 1, this is clearly a spanning set for R2, right? The set one, the vector 1 0 and 0 1 spans R2, but can you think of another spanning set for R2, something which is different from 1 0 and 0 1, right? So in fact any two linearly independent vectors can span R2. You can take 1 2 and say 5 3. These two vectors also span R2. And why is that the case? So you should be able to write V, any vector V, v1 v2 as some linear combinations alpha times 1 2 plus beta times 5 3, right? Or in other words, this is 1 2 alpha beta, and since this vector 1 5 2 3 is invertible, you can also, irrespective of what v1 and v2 are, you can always find appropriate values for alpha and beta, right? So clearly this any linearly so in general for to get a spanning set for R2, any set of any set of vectors, at least of linearly independent vectors, spans any set of at least two linearly independent vectors spans R2. So while this is a spanning set of R2, is this a spanning set for R2? So is this spanning set for R2? Yes, it indeed is. So because you can write every vector in R2 as a linear combination of these three vectors, right? So in general, if you have any spanning set for a vector space, then if you add more vectors to this set, then it still remains a spanning set, right? Because of this linear combination gives you R2. Then linear combinations of more vectors can obviously get you to any vector in R2, right? So when I say that every vector V can be written as a linear combination of V1, V2 up to Vn, this linear combination need not be unique. There should be at least one linear combination which gives you the vector V, right? So a spanning set is any set of vectors which through linear combinations can get you to any other vector in the space. So on the other hand, a basis for a vector space is the smallest such set. So it is the smallest spanning set for a vector space. So a set V right. So we say that V1, V2 up to Vn is a basis for V if it is, well, there are two different ways of putting it. If it's either a minimal spanning set of V. So when I say a minimal spanning set, if I remove any vector from V1, V2 up to Vn, if I throw out any of these vectors, then it doesn't become a spanning set for V, right? So this is one way of defining the basis. The other way of defining it is if it is a linearly independent spanning set. So it spans V, and in addition all vectors are linearly independent. So let's go back to these examples that we had over here for R2. So let's look at this set of two vectors. If I remove either of these two vectors, then the vector is then it's no longer a spanning set for R2, right? So obviously this set forms a basis. Also, also these two vectors are linearly independent and they span R2, and therefore it forms a basis. The same holds for this, right? But what about this example over here, the third example? Clearly, if I remove any of these, if I remove any one of these three vectors, then it still remains a spanning set for R2, right? Because I can get any vector in R2 by a linear combination of any two of these three vectors. So therefore, this is not a basis for R2. But if I remove any of these vectors, then it becomes a basis for R2. So for example, if I delete this vector, then the other two vectors put together gives you a basis for R2. Also, these three vectors are not linearly independent. You can always write one of these vectors as a linear combination of the other two vectors, right? So therefore, if you think about it intuitively, if you go back to the matrix representation, what is our requirement? So we should be able to write any vector v as a linear combination of v1, v2 up to vn. So if each of these are column vectors, then I should be able to get some coefficients. C, let's call the coefficient vector C. So I should be able to write V as a linear combination of v1, v2 up to vn, or in other words, in the matrix form, I should get V to be equal to this matrix, capital V times C, right? Or let me call it A times C, just because we're using too many V's. Right, so we have V equal to A times C. For V1 through Vn to form a spanning set, then there should exist at least one solution for C. So V equal to AC should have at least one solution, because otherwise, if there is no solution, then it means that you cannot get V by a linear combination of V1, V2 up to Vn, right? So if this has greater than or equal to one solution, then it's a spanning set, right? So what about a minimal spanning set? So for a basis, the set of vectors should also be linearly independent, right? So in general, suppose that we have suppose that A is an m by n matrix, then for this to have at least one solution, m should be less than or equal to n, right? If m is larger than n, then there will always be vectors v which cannot be written as a linear combination of the columns. M should be greater than or equal, m should be less than or equal to n for this to have a solution. M should be less than or equal to n in order to have at least one solution always. So irrespective of what v is, we should always be able to find a C, right? So the only way that can happen for every v is if m is less than or equal to n, right? Now, in addition to requiring this, we must also, for v1 through vn to form a basis, the vectors v1 through vn should also be linearly independent, right? And you know that for v1, if v1 through vn have to be linearly independent, then that can happen only if n is greater than or equal to m, right? And we'll see that why that is the case in maybe a minute, right? So for it to form a basis, you need to have m to be equal to n, and the vector should be linearly independent. So in terms of the number of solutions, there should be exactly one solution. So v1 through vn forms a basis if v equal to a times c has exactly one solution always. So if v equal to a times c has at least one solution for every v, then C is said to be a spanning set. Then this set v1 through vn is said to be a spanning set if it has exactly one solution for every v. Then v1 through vn is said to form a basis, right? So a remarkable result in linear algebra is that no matter which two bases you take for a subspace, so clearly the basis, as we've seen in this example over here, the basis of a vector space is not unique, because for R2 we know that this forms a basis, we also know that this forms a basis, right? But what is special is that these two bases have the same number of vectors. So if you take any two bases for a vector space, then they will have the same number of vectors, and we'll assume here that at least one of these bases has a finite number of vectors. So we'll only consider vector spaces which have a basis of finite size. So suppose that you have two bases, v1, v2 up to vn. Okay, suppose that this is one basis for a vector space, and we have another basis u1, u2 up to um, right? So let me call this set capital V, I'll call this set capital U. So suppose that both of these form a basis for the same vector space. Then what our goal is to show that n is always equal to m, and I state that this is pretty obvious. And why is that the case? So you should be able to write, in order for this to be vector space, every vi, you should be able to write every vi as a linear combination of u1 through um, right? So since u forms a basis, you should be able to write each vi as this matrix u1, u2 up to um times some coefficient matrix. So each vi can be written as some coefficient as this matrix, let's call it B times C. So each vi can be written as, let's call it Ci of the ith matrix, right? And similarly, you can write each ui as, or uj as A times, call this Cj prime, where A is v1, 2 up to vm, right? So now can you say, so but what do we know about the vi's and the uj's? We know that v1, v2, v3 up to vn forms a basis. So in particular, they span the space, and they're also linearly independent, right? So v1 through vn are linearly independent, and this in particular implies that, so if v1 through vn are linearly independent, and say u1 through um are also linearly independent, and you can write each vi has a linear combination of u1 through um, then I claim that if this is satisfied for all I, and the vi's are linearly independent, then it must mean for this to have a solution, always have a solution, m must be greater than or equal to n. And similarly, for this to happen for every uj, n must be greater than or equal to m. Because if you cannot do this, because v1 through vn are linearly independent, and if you can generate each vi using fewer than n linearly independent vectors, then you will arrive at a contradiction. So these two together imply that m must be equal to n. So in other words, to summarize, if you have a vector space or a subspace which has n vectors in a basis, which has one basis with n vectors, then every other basis for this subspace or vector space must have the same number of vectors. And the number of vectors which is unique for a subspace is called the dimension of the subspace or the dimension of the vector space. So for example, if you take R2, then every basis for R2 must have exactly 2 vectors. It cannot have fewer than 2 vectors or greater than 2 vectors. If you remember, we defined the field F2, which consists of the set 0, 1, and the addition was binary XOR and multiplication was binary AND. If you look at F2 square or F2 cube, then this has exactly 3 vectors in any basis. So the dimension of F2 cube or F2 3, that is a set of all vectors of length 3, which with each element coming from F2. So this has dimension 3. Similarly, so now can you tell me, if you look at the set of all m by n matrices, so the set of all m by n matrices forms a vector space, and what is the dimension? So the addition the addition of the vector addition operation is component wise or element wise addition, and it's a standard scalar multiplication. Now for Rm by n, can you tell me what the dimension of this vector space is? Think about it, right? So a similar so another vector space is the space of polynomials. So if you look at the set of all polynomials are x are m of x, so this is the set of all polynomials of degree less than or equal to m, and coefficients from R. So it is a set of all a0 plus a1x so on up to am x to the m. And so for all possible values of a0, a1 up to am, I claim that this is a vector space. And in fact, so what is the dimension of Rm of x? I need to pause the video and think about it. What is the dimension of Rm of x? Right. So the dimension of Rm of x is m plus 1. And this is visually obvious because there are m free variables and each of these can be independently chosen. So the dimension of Rm of x is m plus 1. Right. And here's maybe an interesting example. So if you look at the vector space R over the field Q, so R is the vector space, so you can add the addition of any two real numbers always gives you a real number, and multiplication by a rational number with a real number always gives you a real number. So R over the vector space of R over the field Q is also a vector space. What is the dimension of this vector space? I want you to pause the video for a minute and think about it. Right. So R as a vector space over Q has infinite dimensions. And why do I say that? So clearly, I mean, so initially you may think that the dimension is equal to 1, but that is not the case. So because any irrational number, so for example, if you take root 2, root 3, root 5, 7, so take any prime number, for example, and tell me if you can write alpha 1 root 2 plus alpha 2 root 3 plus alpha 3 root 5 plus alpha 4 root 7 equal to 0. Is there any rational linear combination of these elements which gives you the 0 element? In fact, no, this is not possible. Right? So R as a vector space over Q has infinite dimension, and the way to prove this is that if you take the set of prime numbers, there are infinitely many primes, and you take this, for example, the square root of these, you cannot write so you cannot write any square root of a prime as a linear combination, as a rational linear combination, which is equivalent to saying that you cannot write it as an integer linear combination of the square root of other prime. So now we've seen concepts of basis and dimension of a vector space, so on. So let us revisit the vector spaces of corresponding to a matrix. So given an m by n matrix A, we looked at two different, well actually there are 4 different subspaces associated with the vector A, with the matrix A. So one is the column space, which is the vector space generated by the columns of A. Then there is the row space, so the set of all vectors which can be written as linear combinations of the rows of A. And you have the right null space, which is the set of all vectors x such that Ax is equal to 0, and the left null space, which is the set of all vectors x such that x transpose A equal to 0. Right? So these are 4 fundamental subspaces associated with the matrix A. Now the rank of A is defined as, so typically there are 2 ranks. One is the row rank A. This is the dimension of the row space of A. And similarly, the column rank is the dimension of the column space A. The nullity of A is equal to the dimension of the right null space of A. And so one thing which should be fairly obvious and was also pointed out in one of the problems is that the row rank plus the nullity should be equal to n. Right? So in general, if you have an m by n matrix, so A is m by n matrix, then basically the row space of A is the set of all vectors which can be written as linear combinations of the rows. So this corresponds to some hyperplane, right? And the null space of A, the right null space of A, corresponds to all those vectors which are orthogonal to the row vectors, or in other words, it's orthogonal to the row space. right? And what is the dimension of that? That is going to be n minus the row space of A. So nullity of A is equal to n minus the row rank of A. So the row rank plus nullity is equal to n, and that is geometrically pretty obvious, because for example in 3 dimensions, if you have 2 linearly independent vectors, or if you have a vector space of dimension 2 which is a plane, then the set of all vectors which can be orthogonal to this plane is a line, right? In 2 dimensions, if you have a line, then the set of all vectors which are orthogonal to this line is another line, so it's a perpendicular line. And similarly, if you have a single line in 3 dimensions, then the set of all vectors orthogonal to this line corresponds to a plane. Right? So that is pretty obvious, and it's geometrically very intuitive. What is perhaps a little more surprising is that the column rank of A plus the nullity is also equal to, so the column rank and nullity are also related. In fact, we will show that the row rank is always equal to the column rank of A. So in the very next lecture, we'll see these very fundamental concepts of the fact that the row rank of A is equal to the column rank of A, and the row rank of A plus the column rank of A plus the nullity is equal to the number of columns.